Continue. This meeting is being recorded. Okay, welcome to our data mining class. Whether you are celebrating or mourning the election, we get to sober ourselves up with some nice, fun mathematics today. Totally clear of politics and other stressful things. There's a notes packet up front. If you like printed things, the corresponding PDF file is in a new folder, topic 5, in our repository here, this notes.pdf. We may or may not get to that file today. We will find out. Last time, we drew a whole bunch of scary pictures and had a whole bunch of new notation. And many people were appalled about the fact that the same English words can refer to different mathematical notation, different mathematical objects, different mathematical things. And that's, again, for two reasons. One is that this is a new field. We haven't had time to settle on the notation and language that we use. All the people who invented this stuff, not all but one, still alive. So yeah, things are still in flux, but really the bigger picture reason why two mathematical objects might share the same English name is because they are really representing the same information. Let's back over here, submit that. And so the main example, there's two main examples of how this has come up is that our textbook uses generalization error to refer to the difference between the out-of-sample error and the in-sample error. But other people sometimes use generalization error to refer to the out-of-sample error only. And it's you just have to either know from context which is which or clarify looking at their mathematical notation. The textbook and me in class, I always refer to generalization error. Probably 80% of machine learning, data mining people always refer to generalization error as this difference right here. But a handful of people, especially people on the less technical end of the data mining spectrum, will call the out-of-sample error generalization error. That hasn't been a huge issue for us so far, but this approximation error one here, this is one where we do have two separate notations that we've been using in class, two separate mathematical objects that have the same English language name. That in not the homework that was due this past weekend, but the previous one with the, or maybe it was the one that due this past weekend, I forget. But one of the homeworks defined the approximation error with the way that, one way of doing it. And that approximation error was this gray dashed line right here, this gray dashed line, which is the intuition about this approximation error. It is the error that only depends on the hypothesis class that you select. So this scripty F, capital funny looking F, this is Leon-Buteau's notation for a hypothesis class. Hypothesis, again, synonym for function. So F and H, whether you're talking about functions or hypotheses, it's the same thing, but people who use the word function tend to use F. People who use the word hypothesis tend to use H, but very, very similar, or in fact, exactly the same thing. And the approximation error, the big picture idea of it, the why do we care, is that it captures the error fundamental to that hypothesis class, irrespective of the amount of data that you're using. So as your in value over here, the amount of data that you're using goes to infinity or goes to 0, your approximation error stays the same. The version of approximation error, though, that Leon-Buteau uses is he uses the difference between this dashed line right here, the approximation error as we defined in the homework, and the Bayes error. And so his approximation error is, he uses the scripty E, APP for approximation right here, is the difference between the gray line and the black line right here. This difference still captures somehow fundamentally that same information. It is still like the only thing that it depends on is your actual hypothesis class that you select. And if you select a different hypothesis class, you get a different approximation error. And it does not depend on your your number of samples in any way. And so it's somehow capturing essentially the same information, even if the mathematical definition is slightly different. And so that's why it is customary or common to call both of those things the approximation error. The approximation error is the error that is independent of the amount of data that you have. Okay, so we talked about a bunch of different types of errors last time, drawing all these curves. The optimization error is really the new error that we talked about last time, and this is the error that is not statistical but computational, that we have whatever our loss function is. It looks like I drew it in red right here, this E sub n, our in-sample error with the weights on the x-axis down here. And as we change what those weights are, again, there's a one-to-one correspondence between weights and hypotheses. As we change our weights or change our hypothesis, we will get a different in-sample error. And the idea of gradient descent is somehow rolling downhill of this in-sample error, trying to find this minimum. And if we were to have infinite computation, then we could achieve this minimum, but we never have infinite computation. We have some finite amount of computation, and so we get close. We can get as close as we want, but we can never quite exactly get there. And that difference there is our optimization error. The Leon Bateau, the thing that he's building up to, the reason we talked about these errors is because your final error, whatever your final error is, you can break it down into three terms: this optimization error plus the estimation error plus the approximation error. So these three terms right here describe or capture all of the ways that error can come into our problem. Coming back over to the Leon Bateau's actual paper now, everything that we talked about last time, drawing all of these pictures, is described in detail in this one paragraph summary right here. And yeah, that's for me, this one paragraph summary is very readable and understandable. If for you at this point it's not very readable, but that is the goal, to be able to see these one paragraph summaries of notation in a paper like this and be able to understand how whatever that notation is, understand how it correlates to the different types of pictures that we've seen so far. One of the reasons I selected this paper, we already talked about, is that this is a historically important paper. So it came out in 2011, just at the time when big data was becoming a thing, and just at the time when stochastic gradient descent was becoming a popular tool in machine learning. And this paper here captures all of the enthusiasm that people had about stochastic gradient descent and why we cared about it. So that's one reason. The other reason why I selected this paper is because notationally, between the notation of this paper and the notation of the textbook, all notation of machine learning is represented. Yeah, things are slightly different in this paper, like using S instead of H's, using slightly different definition of approximation error, various slightly different terminology that way, which is in some sense frustrating. But again, the purpose here, one of the purposes, is to help get you comfort with those different terminologies, because you will see people use them in practice in those different ways, and you will have to be able to adapt. Okay, so that's our summary of what we did last time, where we've been so far. And what we're going to do today is we're going to finish off this paper here. We're going to talk about the why we care. And I stated this as a fact last time, but we didn't actually talk about why this is the case. But that there are two regimes two computational regimes that we care about in machine learning with these problems in this optimization arena. And one is if we're in these small scale learning problems. Again, everybody before 2010 was in this small scale learning problem world. And this means that our n value, the number of data points, is small, so we are not limited by computation. And what it will turn out to be the case is that either first gradient descent, 1 GD, or 2 GD will be the optimal algorithm here. So we haven't talked about why that's the case yet, but this is what we're going to explain today, this stuff in red. And then in the opposite situation, large-scale learning problems, when our n value is very, very large, then we will be limited by computation, and it will turn out to be the case that stochastic gradient descent will be the optimal optimization algorithm to use. Okay. Everyone's that's properly prepared us, put us in the mood to dig into data mining and math for today? Okay, I see one head nodding, so that means gives me permission to plow forward. So this section 3.2 here is what we're gonna, it's the last section that's important for us to cover in this paper, and it's really what the other sections we're building up to, why we care about this paper. And what we're going to start with is this table right here, table 2. And I have this table reproduced in the notes packet as well. And so it's a little bit bigger over here, and we will start our discussion looking at it in this notes packet. So the idea of this table 2 is that it is summarizing all of the computational information about these 4 different algorithms. And this is summarizing in the same sort of way that we talked about computational information about PageRank and the perceptron learning algorithm. All 3 of these, or all, I guess, 6 of these, all however many algorithms we've talked about, are you can break them up into sort of 2 steps, their analysis. One is thinking about first, what is their time per iteration? Every time each iteration is one mathematical formula, how long does it take to compute that one iteration, compute that one mathematical formula? And then think about how many iterations do you need to achieve some particular accuracy. This Greek letter right here is rho, and this Leon Bateau is using rho for the computational accuracy that we're achieving. The rho is essentially synonymous with the optimization error. And so the time per iteration here in the Leon Bateau paper, he only is talking about in terms of the number of data points and leaves out the number of dimensions of your problem. So we are going to make this a little bit more accurate by also specifying the number of dimensions. We talked about with the gradient descent formula that you are only computing, there's no matrices involved, only vectors involved. In the BLAS world, those are only BLAS 1 level operations. And so everything is running in linear time, and it's a single D in front of the N right here. So it's our computation is D times N. That was different in the 2GD world, where we had this matrix vector operation, this BLAS level 2 operation, and this took time D squared plus D times N for our second order gradient descent. And the intuition, one of the intuitions we talked about with our pictures is that this is a much bigger quantity. The D squared right here is significantly larger quantity than the D by itself. And so each individual iteration is going to take more time. Pictographically, we argued that it's the advantage of 2GD is that we're somehow automatically determining our step size for us. And in the large dimensional case, it's also helping us improve our direction a little bit. And so it turns out that the amount of iterations that you need is much, much smaller. With standard gradient descent, the number of iterations you need is log of 1 over rho. Rho, again, is the accuracy that we're trying to achieve. And so rho is going to be some small number less than 1, like 0.01. So that we'll have the log of some number larger than 1, which will make sense, give us a positive number here for the number of iterations that we need. And in second order gradient descent, it's significantly faster, exponentially accelerated with an additional log factor up here. So 2 logs instead of 1 log. So many, many fewer iterations, but each iteration taking more time to actually compute. The number of iterations does not depend on the dimensionality at all or on the in value at all. So this the second line right here, totally independent of both D and in. The time to accuracy row is just multiplying these quantities together. And so with what Leon wrote, he has in log 1 over rho for the time to accuracy row of gradient descent. That's just multiplying the first row, the time per iteration, times the number of iterations, getting the in value here, adding in our D factor, gives us this D factor up in front as well. For second order gradient descent, it's still the same thing. Multiply these first two rows together. We get this third row down here. It's just that we'll have to add a little bit of parentheses, doing D squared plus dn like that right here. All of this discussion should hopefully be somewhat reminiscent of our power method discussions, exponentially accelerated power method, and the PLA, how we did the run times of all of those. Okay, so that's gradient descent and second order gradient descent. What about stochastic gradient descent? Well, we also said that the difference between stochastic gradient descent and regular gradient descent, I'll remind us of the formulas coming back over to the Leon Deteau paper, scrolling up just a little bit. So the gradient descent formula here has this big summation inside of it, this 1 over n times the sum of n. This is where the runtime in factor comes from. But the key idea of stochastic gradient descent is rather than averaging all of those gradients together, we'll just pick one at random. And so there is no 1 over n sum of in factor in stochastic gradient descent. There is no dependence on the number of data points. And there's still dependence on the dimension. That computing this gradient over here takes time d. And so our SGD right here is going to be a d, or d times 1. Second order stochastic gradient descent, we still have that matrix going on, this uppercase gamma right here, this Greek letter, the uppercase gamma, but no summation. This is a vector coming out of this gradient method right here, vector times the matrix. We still have the d squared operation. And so it's d squared right here. I guess one thing to note too that I haven't explicitly said is that all of the notation here is implicitly in big O notation. And there's just would be a lot of O's if we were writing them all out. And so made that asymptotic notation implicit here instead of explicit. But all of this is only in the limit case as the amount, as these variables go off to infinity, ignoring constant factors. Okay, the number of iterations to accuracy row. One of the interesting things is that when you go from gradient descent to second order gradient descent, you get this extra log factor in your number of iterations. So second order gradient descent requires many, many fewer iterations than gradient descent. That turns out not to happen with stochastic gradient descent, that both SGD and 2SGD have this 1 over rho as their number of iterations that they need, and there is no log factors in either of these. And both of these two values are exactly the same. There's, again, explaining why that's the case would be at least a semester, maybe more, of optimization. And so we're just focusing on the result right now. The result is the thing that you need to know for this class, and not the detailed mathematics of why this is the case. And then doing these multiplications together, we get the time to accuracy row as d over rho for SGD and d squared over rho for 2SGD. One of the things to note at this point is that SGD completely dominates second order SGD. That, and okay, we haven't talked about this last column as well, but it'll be true in this last column as well, that SGD here is always better than second order stochastic gradient descent. SGD always better than 2SGD. And so it never makes sense when you're trying to select an optimization algorithm. It never makes sense to select second order stochastic gradient descent. And nobody does this, not in machine learning, not in any other like mathematical discipline. If we're comparing gradient descent, though, versus second order gradient descent, there is some trade-off because gradient descent has the better dependence on the number of dimensions, and second order gradient descent has the better dependence on the accuracy rho, and so neither one of these strictly dominates the other. If we're looking only at this row right here, time to accuracy rho, then this is what people were doing previous to 2011. So less than or equal to 2010. This paper coming out in 2011. Some of the main ideas of this paper coming out between, say, like 2006 up to 2010. But 2010 here is a nice convenient number to mark as the exact turning point. But less than or equal to 2010, people were saying that we always want our accuracy, always want our rho to go to 0. Always want rho to go to 0. Rho, again, being essentially our optimization error. And in that case, neither SGD nor 2SGD makes sense. That if we're trying to make our optimization error here, our rho, go down to 0, which seems like a very reasonable thing to want to do, then gradient descent and second order gradient descent guaranteed to be faster. Looking at this notation over here, all three of these columns right here have at least a D factor in their, at least a D factor in their formula here. SGD has 1 over rho by itself, no log factors. That's significantly bigger than log of 1 over rho, which is significantly better than log 1 over rho. So less than or equal to 2010, people will always saying we should make our optimization go down to 0 as close as we can get to 0. And that implies that SGD never used. SGD never used. Only gradient descent or 2 gradient descent. This is a good spot for us to pause for a second and check in with questions. There's an important point to realize here, that only looking at this time to accuracy rho, if we're actually trying to make our rho get really, really small, go down to 0, then neither of the stochastic algorithms make sense. Only gradient descent or 2 gradient descent makes sense. And which one of those you want to do depends on how D and rho relate to each other. Are we all tracking? A couple of head nods. Okay, the key observation of this paper and the reason why we talked about all of these fancy graphs up here is that at some point increasing your accuracy, your optimization accuracy, so increasing the optimization accuracy is equivalent to saying having rho get smaller, having e-opt get smaller. At some point, making that smaller does not provide you any benefits. So the realization greater than 2010 is at some point making rho smaller gives you no benefit. And why is that the case? Well, our error, our final error of our problem can again be broken down. So the E equals this E approximation plus the E estimation plus the E optimization. is the breakdown that we had before. And so our E optimization, this is going to be row over here. And if these two values, our approximation error and our estimation error, are very large for whatever reason, which is, as we've talked about in the talking about chapter 2 and 3 of the textbook, it's very common for our approximation error and estimation error, or equivalently our generalization error and in-sample error. It's common for those to be very large, and making your optimization error row go significantly smaller than that is not going to improve your generalization error, your out of sample error in any way. So Leon Bateau, down here in 3.2, what he's describing is that with this formula, plugging in the row for the optimization error, this term right here is that estimation error. It's the VC dimension bound. Generalization error from VC dimension. He's treating the VC dimension itself as a constant here, and only considering the dependence on in right here. And we're going to set all these things equal to each other in a complex formula here in a second, and solve for how much our row value over here should actually, what it should actually be equal to, depending on our in values. And that's where this time to excess error is going to come into play. This last row. We're going to notice that this last row coming up here, this last row up here has no dependence on our in value, no dependence on our dimension, no dependence on our row values in any way. It only depends on this excess error. And we'll derive this in a second, but we'll be setting all of these formulas equal to each other. This E estimation, again, that square root of log in. He keeps the log factor on top, log in over in, and the row. We'll set all these things equal to each other, solve for the estimation error, and we'll get these values down here. Let's see. So in order to do that, the stochastic gradient descent is fairly easy to do that for, because there's only the row value here and their dependence. And so setting row equal to asymptotically our estimation error. So for SGD, the only thing that we have to do is setting row tilde E. The tilde notation in the Leon Bateau paper, that's equivalent to saying rho equals theta of E. So a notation that we haven't used yet, but that's the concept behind that is something that we've seen a lot. The tilde, just a shorthand notation for these two things, are asymptotically equivalent to each other. So rho tilde E, and we do that and can substitute up here for the rho and the epsilon, and we get our time to excess error. Just depends on the epsilon value up here. For the gradient descent and stochastic gradient descent, we do that same equivalence to get rid of rho. And when we do that, we get a 1 over epsilon inside the log over here, and then a 1 over epsilon inside the log factor right here. Log 1 over rho becomes the log 1 over epsilon. For gradient descent and stochastic gradient descent, to get rid of the in values, we also have to set, apologize, I pressed a button that jumped my page. For gradient descent and 2 gradient descent, GD, 2 GD, we also need to do the in values, solve for in over here. And the way they do that is E equals the square root or tilde square root of log n over n. So that implies that the epsilon squared tilde log n over n. And this being a little bit awkward to solve algebraically, but that'll be n tilde 1 over epsilon squared times log epsilon, like that. The jump from this line to this line, why it's true is, yeah, again, algebraically awkward, but that's the final jump right there. Plugging this value into the n value up here, plugging it into n gives us the final formula down here, doing that substitution. One last algebraic subtlety here is that notice there's not a 1 over there's not a 2 right here, there's an alpha right here. And the reason for that is Leon Bateau says that they want their alpha to be within 1/2 to 1. The 1/2 case right here, this is the case that we've talked about as binary classification. The 1 here case, this is the section that we skipped from the textbook, 2.3, I believe, and that's in the regression setting. The textbook derives a bound that has a 1 as the exponent there instead of a 1/2 as the exponent here. So just to be a little bit more general, Leon Bateau uses alpha right there, but yeah, we can use the 2 value right there instead, for the alpha 1/2, meaning 1 over alpha being 2. And so that's how this time to excess error is derived. That the key idea here being, again, that we're not making our rho value go down to 0. We're making our rho value go down to whatever it needs to be so that our optimization error matches our estimation error, which matches our approximation error. And in that case, we get these 3 formulas right here, or these 4 formulas. We have these 4 formulas right here. Looking at these 4 formulas, what you'll notice, the big picture takeaway here is that, let's see what color, go orange. This is smaller. The time to excess error for SGD is smaller than these. So SGD smaller than both gradient descent and second order gradient descent. It's smaller for 2 reasons. One, because we don't have these extra log factors that we're multiplying against. And it's smaller because the exponent down here in the binary classification case is, we're doing epsilon squared, which takes a small number, makes it much, much smaller, and so makes the reciprocal of that larger. So stochastic gradient descent, when you are not trying to make rho go to 0, but try to make rho go just to whatever you need to match your statistical accuracy, stochastic gradient descent is smaller. If you're trying to make rho actually go to 0, though, the gradient descent bounds are smaller. That if rho is actually going to 0 instead of just to our excess error, this E value, this out of sample error, then gradient descent or stochastic gradient descent is faster. Question?
So you're saying you want to set rho to the total error, or to the total error is made up of 3 parts? So what do we...
Yeah, so we're saying that all 3 of these parts are going to be asymptotically set to each other. And because it's asymptotically set to each other, like you're ignoring the constants. So setting rho or E opt asymptotically to epsilon, you can think of that, okay, let's just make it 1/3 our excess error right here. And E estimation, that's also 1/3 our excess error. And the approximation error, that's also 1/3 of our excess error. But because we're in this asymptotic world, the theta notation world, we can just then drop all those constants and just say that we're making the optimization error go to the excess error.
So all four of them are asymptotic, or we were setting them to.
Exactly. And in the big data world, this is what you want to do. If you are computationally limited, then you don't want to run your row down to 0 because that'll take too much time. And you just make your rows small enough that that it sort of doesn't matter anymore. If you're not computationally limited, you may as well just make your row go down to 0. So if you're not computationally limited in the small data world, then using gradient descent or stochastic gradient descent still makes sense. It's actually the thing that is most commonly used still today. If you're in the small data world, if your, say, n value is less than 1,000, then these are definitely the things that everybody will use. If you're in the big data world, then where computation does matter, there's not a hard threshold, but definitely if you're in the billions of data points, computation is starting to matter. And so you're in this world where we don't really care about getting the exact minimum. We just want our minimum to be close enough that it no longer matters statistically, that it's asymptotically the same as our estimation error or approximation error. Okay. Let's see. So there's 3 problems here, very real world oriented problems that use this, the information from this chart right here. And so we'll go through at least the first one of these problems today, and that will hopefully make this theoretical stuff more concrete. These real world problems, again, down here, these are the things that for your final exam, you should be focusing on how to solve. And everything else that we've talked about is just the background needed to be able to actually solve these problems. So problem 4 here, you're training a logistic regression model using the polynomial feature map with a very high degree and a small number of data points. And the question is, which optimization algorithm do you choose and why? Well, the first observation here is that because it's a small number of data points, in small, this will imply that we are not computationally limited. And so that implies we can make our row value go to 0. Maybe as an aside, I've always been using, when I use the double arrows like this is to indicate a logical implication. And when you use a single arrow like this is to indicate that the limit, we're interested in the limit as this variable on the left-hand side row goes to 0. So we're not computationally limited, so we care about the case of row going to 0. And that implies that we're not going to want to use SGD or 2SGD. We're going to want to use gradient descent or stochastic gradient descent. GD or 2GD. 1GD or 2GD. Anytime you're in this small data regime where it's physically possible to make your optimization error go down to 0, we want to use the algorithms that are going to get us the fastest there. And so that's considering this third row here. This third row is what you consider when you want to make row go down to 0. And so these are our 2 formulas that we'll have to consider: dn log 1 over row and d squared plus dn log 1 over row. In order to, decide between those, let's copy down those 2 formulas right here. So gradient descent was d times n times log 1 over row is the runtime, overall runtime for gradient descent, combining both the runtime per iteration and the number of iterations into one formula. And the second order gradient descent right here is the d squared plus dn times the log of 1 over row. And now we're in this situation where in order to select between these 2 algorithms, we have to consider our trade-off between the number of dimensions and our row value. There's another situation where there's like not hard and fast numbers that you use to decide which one of these two techniques to use. And the intuition is just if D is somehow very small, if D is small, this will be the optimal thing to do because the D squared over here will not dominate, and the log 1 over rho here will be smaller than the log 1 over rho here. But if D is large, then the D squared factor over here becomes dominating and not the right choice anymore, because the D squared will become larger faster than the log 1 over rho becomes smaller. This is again a very intuitive argument. There's no, like, you can't say, okay, 10 dimensions is large or 1,000 dimensions is large. There's no like crisp line here. But up here in the prompt for the problem, I'm specifically saying that the feature map is a high degree, which means that our dimension coming out of that is going to be significantly higher degree than that. So we are definitely in the high degree range over here. And because we are in the high degree range, so this is the problem we're at. So problem says D is large, so use this. That's what I'll write. Use 1GD. This is the style of reasoning that you will have to be able to do on your final exam. So are there any questions about this style of reasoning? Clear as mud to everybody? Your next homework assignment, coding homework assignment, will start exploring some of these trade-offs for you a little bit so that you can get a little bit more practical intuition about these things. And this is the style of reasoning, what you need to be able to understand for the final exam. Okay, part 2 down here. So part 1 about the runtimes, optimization, what to select. Part 2 about the statistics here. And so it says, does VC theory predict good or bad statistical performance? And what we have, based on the problem statement, is that our DVC is large. The reason for that is because the Q is large in the polynomial kernel. But our in value is small. The number of data points is small. And again, our generalization error being the O of square root DVC over N. This implies that we are in a bad place for generalization error. Our VC dimension here being very large at the top over here, and in denominator being small means this overall term here will be large. And so bad, let's see, bad statistical performance. It turns out that if you are actually in the small data regime and in a situation where you should be getting good statistical performance, then it never makes sense to use one GD. So small data regime, small data regime plus good statistical performance implies that 1GD never optimal. 1GD never optimal. The good statistical performance here, implying that the VC dimension down here, or the dimensionality of our problem space, is very small. And so because the dimensionality of our problem space is very small, it means that the log term over here is going to dominate instead of the d squared term. And so second order stochastic gradient descent will be the better solution. If you're in the large data regime, then the 1 SGD is the tool that you'll always want to use. 1 SGD is always the right optimization is always correct. Again, we don't consider 2 SGD because 2 SGD is strictly worse than 1 SGD in all situations because it has this quadratic factor in the dimensions. And so for machine learning, for data mining, for these statistical applications, the only algorithms that you will should ever select are either 1 stochastic gradient descent or 2 gradient descent. And 1 gradient descent will never be optimal. 2 stochastic gradient descent, never optimal. Yeah, so there's for machine learning, the choice is always between 2 GD or 1 SGD. In other fields where statistics is not a consideration the same way it is in machine learning, as we've been talking about it, this might not be the case, but for us in particular, 2 GD or 1 SGD are the only algorithms that ever make sense to use. 1 GD or 2 SGD never makes sense.
So then what would we do earlier? Because we chose to use 1 GD.
So the question is, up here we selected 1 gradient descent, and why is that the case? So the computationally, 1 gradient descent here is going to be the correct thing to do. It will be the fastest algorithm. But if you are using your statistical reasoning correctly about setting your VC dimension properly, you will never find yourself in this situation where you have a large dimension and a small number of data points. That's the key thing that made 1 gradient descent correct to use optimization-wise up here, is we had a very large dimension, but a small number of data points. That does make 1 gradient descent correct. But if you're in that situation, you're guaranteed bad statistical performance, and so you never want to find yourself in that situation. Ultimately, the only thing that we care about is our statistical performance, and the runtime is just a sort of side effect that if we had infinite compute, then it wouldn't matter what algorithm we selected. We would only care about these statistical properties. And as we're deciding like which algorithms to use, we always start, which models to use, we always start with the statistical considerations, get ourselves in a good balance space statistically. And once you have done that, you will find that it never makes sense to do 1 SGD. So again, if you're in the small data regime and you're getting good statistical performance, 2 SGD is optimal, 1 GD never optimal. The reason we selected gradient descent is specifically because we're in the bad statistical performance regime, which we don't want to be in the first place. Okay?
Oh yeah, so you mentioned earlier that this model is bad statistical performance because generalization error is high.
Yes.
Wouldn't it be equally bad if it was too low?
Question is, would the statistical performance be bad if the generalization error was too low? And possibly that we have this intuition about there's this trade-off between generalization error and in-sample error. And if our generalization error here is getting really, really small. That suggests that our in-sample error is getting large to counterbalance that. But the problem here is not talking. It doesn't mention the in-sample error in any way. And so it could still be the case that the in-sample error is, for example, 0 in either of those situations.
Then out-of-sample error would still be high.
If our in-sample error is 0 and our generalization error is large, then the out-of-sample error would still be large, yeah. Okay, there's 2 more problems in this packet here that are just going through different situations of different combinations of data point size and feature maps and so on. And so we're not going to do those in class. I'll let you work on those by yourself, but these are very much the style of questions that you need to be able to answer to pass the final exam. So very important questions right here to work on. And they are, in general, just combining the things from your midterm exam with this additional consideration of optimization performance right here. Okay. So next in class here, what we're going to do is we're going to shift over to this next set of notes, the chapter 4, starting chapter 4, overfitting. And this again in the repository over here is this topic 5 section notes.pdf right here for the electronic version. Chapter 4 is called overfitting. We've already talked a lot about overfitting in different situations, and we've really already covered everything in section 4.1. Section 4.1 uses specifically focuses on regression cases in one dimension, showing you some plots that you can maybe use to grasp overfitting versus underfitting a little bit more intuitively. So it's worth reading through, but there's nothing that we're going to talk about that's directly going to come from section 4.1. The main thing that we're going to talk about for this chapter is section 4.2, which is regularization. And there's going to be at least 3, maybe 4 equivalent definitions, equivalent ways of talking about regularization, and they are all going to tie back into each other, kind of doing the same thing somehow. But this first type of regularization that the textbook talks about is what's called a soft order constraint. A soft order constraint. And the idea here is that when we're computing our G function right here, the argmin over our in-sample error, instead of considering all possible hypotheses in our hypothesis class, we add this constraint to the optimization problem. This omega, this Greek letter right here is called omega. It's a capital omega. It's a function that takes our hypothesis classes into an R value, a real number, and it's called the regularization function. And what it does is it somehow measures how complicated our hypothesis class is. This is equivalent to defining a new hypothesis class, a new hypothesis class from the old one. In the following way, which I'll explain. And I will use the perceptron as a concrete example. So the original perceptron, our hypothesis class, looks something like H equals X into the sign of W transpose X, where W is contained in R to the D. I'll leave a little bit more space over here. And we've talked a lot about this, talked about the VC dimension about it, various other properties about it. We've seen it a lot. This additional constraint over here, this subject to constraint, what it's doing is inside of this hypothesis class, add an additional constraint on what these W values are allowed to be. So not only must they be in R to the D, must they be some sort of vector, but this omega of W, let me clean that up a little bit. Omega of W must be less than or equal to this C constant value. Pictographically, what this looks like is that so if we draw out our weight space here in 2 dimensions, W1 and W2, the blue hypothesis class, the original perceptron hypothesis class, these were allowed to have W's contained anywhere in the space. There's no restrictions on where in this space these W's are allowed to be. But for the red version, with this additional constraint over here, we're going to be limited where in this space our hypotheses are allowed to be drawn from. The most common function for this omega is called L2 regularization, and that's equivalent to drawing a circle in this hypothesis space with the radius equal to C. And now in this red version, all hypotheses must be inside of this circle. So let's see. One thing that we can immediately talk about from this picture is a subset relationship between these new hypothesis classes up here. I'll add a C subscript to this H sub C, the C determining this C value over here about how big this radius is. And our H sub C H sub C value, I'll do H sub C1, is guaranteed to be a subset of H sub C2 if C1 is less than or equal to C2. So we have 2 different radiuses of where we're selecting from, the C1 and C2. And if our C1 value is less than C2, then we can clearly C2 has more flexibility in where we are allowed to select our hypothesis from. So as one implication of this again is that as the C value decreases, so our C value, our radius here getting smaller and smaller, that will imply that our in-sample error is going to increase. This following that subset relationship about these hypothesis classes. One thing that we're not quite ready to talk about, but an important follow-on implication, which is suggested by this part in blue, is that the changing the C value will also change our generalization performance. And in particular, as C value decreases, our generalization error, that will imply that our generalization error will decrease. This doesn't immediately follow from the VC dimension because, again, the VC dimension is only about shattering one particular data set and not all data sets. And so as we make this radius smaller and smaller, there will still be some data set down here in the middle of the same size that will be allowed to shatter. We won't be able to shatter those data sets on the outside of these circles, but we will be able to shatter data sets on the inside of these circles. And so C decreasing will not affect the generalization, will not affect the VC dimension, but it will have some impact on the generalization here. And so C, let's do a better color than green. Another impact of C decreasing, that will imply our DVC will stay the same. one second. So the big picture idea, what we're going to be talking about in this section of the textbook here, getting back to statistical properties. This will integrate in a little bit more in a few pages with the optimization properties as well. But these types of regularizations, the reason why we're going to be doing regularization is it's going to give us another tool to prevent overfitting or to reduce underfitting. Marco, you had a question?
Why are the hypotheses outside of the circle considered more complex?
Yeah, so this is a fantastic question. The question is that why are hypotheses outside of these circles considered more complex than the hypotheses inside of the circles? And there's not, framed that way, there's not a really good explanation about why that's the case. We'll see here that this version of regularization is equivalent to some other definitions in a little bit, which will maybe draw that link for us, but it's not obvious why we should consider a W value over here to be a more complex thing than a W value over here. In particular, everything that we've said, if we shift these circles to be located somewhere else inside of the space, so for example, to be like very large W's, but still constrained in a circle somewhere out in the space, everything about regularization still holds to be true. So there is this like intuition about like omega is somehow representing the complexity of the hypothesis. But at this point, for soft order constraints, the real like intuition should come from this subset relationship, that changing the C value changes or concretely gives us a subset relationship, and that will allow us to talk about how the in-sample errors and the generalization errors affect each other. But really good question. We will get to that, probably not today, but next class period. Awesome. Another question? In practice, there are 3 of these regularization functions that people use. The L1 regularizer, which is the 1 norm, the L2 regularizer, which is the squared L2 norm, and this thing called elastic net, which is a combination of L1 and L2. So there are other like weird things that people do, but 99.9% of actual uses of regularization boil down to using one of these 3 regularizers here for the omega function, and these are going to be the only ones we consider in class. Let's see. We have about 10 minutes left, but I think this is a good stopping point for us for today. Next time we will talk about these other regularization functions again. So no homework for the weekend, no quiz that you'll have for next week. But you guys most of you still have the midterm to prepare for, and so this is a good stopping point for us for today. If people do have specific questions about anything that we talked about today, happy to stick around for a few minutes and get those answered. Otherwise, I will see you all either at your midterm or next week.